No, Alistair's going to finish telling us about partition.
So does anybody have a desire to look at any one of these exercises or a solution for any one of them? Let me, it's Thursday afternoon, it's late, so let me just look at the second one, just because it's very elementary and maybe easy to digest. So we want to show that, so if we let mk is the number of k matchings in a graph. If we just want to show that these coefficients are, for the matching polynomial, are log concave, so we want to show that this quantity, this inequality, in fact, this is true with something to spare, as we've seen already earlier, that you can put a ratio of binomial coefficients here. But let's just do, so this is it's an elementary proof. It doesn't require any knowledge of roots or anything, stability properties or anything like that, and arises from the Markov chain analysis of on matchings. So so what we want to do is look at the two sets. And we kind of want to set up an injective mapping from this set of pairs to this set of pairs. Or actually what we'll do is a multi-valued mapping where the out degree from here is strictly larger than the in degree over here. Okay, so we'll do a multi-valued mapping. So the idea is that you look at the structure. Does anybody want to have a go at this?
Map is a graph, right?
Yeah, it's a graph. It's a bipartite graph. So it's going to be this is going to be the set of these pairs, and this is going to be the set of these pairs. And we're going to set up a graph. So actually, we're going to partition this into chunks, same chunks over here, and it'll be the case that between each corresponding pair of chunks, the out degree from here is strictly larger than the in degree here.
It's like doing augmenting paths.
Yeah, right, good. So that's basically it, right. I'll give you the benefit of that. So you got to, if you take a pair of a k+1 matching and a k-1 matching, indeed, when you look at their union, you get a bunch of alternating paths, sometimes they may include cycles. So,
just single edge.
yeah, you get that's a trivial alternating path. Yeah, right. So if we call these right, so let's call a path. Let me suppose this corresponds to blue and this corresponds to red, right? Or dotted and dashed, if you like. So call an alternating path is blue if both its endpoints are blue. Both its end edges are blue. Right? So this is a blue path, right? Because it's odd length and it has one more blue edge than red edge, right? And we call an alternating path red otherwise, right? So if the blue matching is an is a k+1 matching and the red matching is a k-1 matching, we must have two more red paths than blue paths, right? Sorry, which way round did I say? Well, let me say two more blue than red. Really doesn't matter. Two more blue than red. In other words, when we put the two matching together, let me redraw this picture. There must be, you know, two more paths like that than like this. Right? Just by counting. Of course, there may be maybe, you know, a great number of both types, but ultimately there must be two more of these. So I'm going to partition this side into according to how many red and blue paths they have. So this part of the partition, let me call it, you know, ER or something. This has R plus 1 blue paths and R minus 1 red paths. And now I guess you maybe were suggesting, so what I'm going to do to map this any given pair here, I'm going to pick any blue path and I'm going to flip its edges from red to blue and blue to red. So that'll take me from something here to something here where there are R blue and R red. Right? And so the out degree here is R plus 1 because I got R plus 1 blue paths to choose. But the in degree over here is only R because to go back I have to flip a blue path back to a red path. And so this gives me the desired inequality, and in fact it immediately gives me at least a k over k plus 1 factor because I get the ratio of R plus 1 to R. And so slightly open exercise is whether you can also get the other factor you need, which is sort of m plus k minus 1 over m plus k, where m is the total number of edges in the graph.
So you can do it without referring to roots?
Yeah, this has got nothing to do. That's my question for this evening when you go home. Right. So whether you can get by this very elementary argument whether you can get the binomial coefficients in there as well. Okay. Yes.
So if you take the Ising polynomial and transform it so you get roots on the real line, do the coefficients count anything? Do they have any meaning?
You're referring to the coefficients that I wrote up before, or?
Yeah, I think so. Like, I mean, the version you're talking about has roots on the circle, right?
Yeah.
But there's also a version that has roots on the imaginary axis.
Yeah, but I did I did yet another transformation. No, but I was talking earlier about the high temperature expansion. So the coefficients of the high temperature expansion have this log concavity property. I don't know, but I'm not sure.
But their zeros are on the circle.
You can make them on the line. On the imaginary line, and because it's square, I think then you can again bring it back to the real line.
Okay. For the high temperature expansion?
Transformation is that 1 minus lambda over 1 plus lambda.
Yes. So this is the transformation.
Yes. And, but then you have squares.
Sorry, then you have what?
So you have only squared terms.
So it's a polynomial.
Yeah, it's an even polynomial only, yeah.
Then you can make
And you can make it, right.
But then the coefficients are counting these subgraphs.
Yeah.
And they have a similar log concavity property, which you can also prove using a similar type of argument.
Yeah, exactly. Just a generalization of this. Yeah. So the general question about whether, one can, what kind of relationship there is between, this is a very tenuous relationship between Markov chain Monte Carlo analysis and log concavity properties and therefore stability properties. So, I don't have really more to say about it, but that's possibly something we can look at this semester. Okay. I'm going to, in the interest of time, unless anybody has a burning desire to talk about one of these others, I'm going to leave them for the moment, and then if anyone wants to ask me about them, including the ones on the back, which are a little more involved, then I'd be happy to answer those. Let me move on then. Oh, and I should say, by the way, I got some questions in the break. So this this transformation using the high temperature expansion is not supposed to be obvious, right? I mean, I don't expect anybody to believe this without a fair amount of work. And in fact, it's number 5 on the exercise sheet to verify that this is true. And it's a kind of an inclusion-exclusion argument. And so certainly it wasn't meant, that was not, this transformation from spin configurations to high temperature graphs is not supposed to be obvious.
Why is it called high temperature expansion?
Because it's also used, actually in that first part of the talk, I was talking about how to prove the existence of a phase transition for the Ising model. The high temperature expansion is actually used in order to analyze what happens at high temperature, so the fact that the magnetization at the origin goes to 0. So it's used in that context. High temperature meaning low B, and a small value of the interaction.
It converges for those low B, right? So if the graph is infinite.
It converges.
Well, if the graph grows, right?
Yeah.
And you ask, so when this thing converges,
Okay.
then it converges for high temperature
Right.
and doesn't flow.
Okay, so I want to, right, so the rest of what I want to say is about how to use other methods. So we do have this randomized algorithm that allows you to gets a good approximation to the Ising model partition function for ferromagnetic Ising model at all values of the parameters and all graphs. So that's a pretty strong result. And can we do something using other methods to maybe make that deterministic? And and the two methods, remaining methods I want to talk about, are related to the two characterizations of phase transitions that we talked about earlier. So first of all, let's talk about correlation decay. So this is so again, what we expect is that computationally the problem should be easier when there's no phase transition. So no phase transition in the probabilistic sense means that as the boundary goes to infinity, it has no effect on the origin. In other words, correlations between different spins should decay with distance. Okay. So we want to use that in order to get algorithms, at least for some values of the parameters where we have no phase transition. Now there's a beautiful technique due to Dror-Weitz, which sort of solves handles this problem for the Ising model, and indeed for general two-spin systems. At least gives you a path, general two-spin systems. So what we're going to look at is so the Ising model on bounded degree graphs now. So all the degrees are going to be less than or equal to delta. And for simplicity, we're going to look at zero fields. So we're going to look at lambda equals 1, which means there's no bias between zero and between plus spin and minus spin. And so the remarkable fact here is that so for any graph of maximum degree delta, for all beta greater than, so beta between 1 and a critical temperature, a critical beta, there exists a polynomial time I called it an FPTAS, right? So fully polynomial time approximation scheme for the Ising model partition function. So this is lambda equals 1. Okay. So what's this critical value? So this is the critical value. So where the phase transition happens for infinite d-regular trees, infinite delta regular trees. So this is the critical point for infinite delta regular trees. And it's equal to delta minus 2 over delta. So we're in the ferromagnetic regime. There's this beta critical, and we're talking about betas in this regime where we have no phase transition. We have phase transition down here, and no phase transition up here. So wherever there's no phase, so it goes all the way up to the point where phase transition starts. We have a deterministic algorithm. And now, so notice what we're doing is we're relating the computation of this partition function to a phase transition not on on trees of the same degree. So in other words, we're kind of saying that the worst case, in a sense, for this problem is trees. So when the problem starts getting tricky for trees, we get when correlations are no longer decay on trees. That's exactly the point where we can't handle general graphs either.
It doesn't become any better if you know that the magnetic field is not zero, so there is no real phase transition.
Well, there's still on the tree. There's still a phase transition. So when you're on the other side of this, you have a critical field. Okay, so there'll be a phase transition in the field. Okay, and you can't. Yeah, so there's a. I'll say a little bit more about that later, but.
Well, there is a phase transition in this. I cannot pronounce the name. Perel sense.
Pile sense.
Perel sense. The non-uniqueness of the Gibbs measure, right?
Yes.
Yeah, okay.
Yes. Okay. So. All right. So how does the Weitz algorithm work? So there are two steps. First of all, you transform your graph G into a tree, and then secondly, you perform a computation on the tree, and you use the phase. You use the lack of phase transition to argue that that computation. The computation on what could be an exponentially large tree can actually be truncated at a small depth, and therefore computation is feasible. Okay, so now this tree is something that we already saw in one of Nikhil's talks, the self-avoiding walk tree. So I believe this is even the same graph that Nikhil used, because these things blow up pretty quickly if you take something bigger. So the self-avoiding walk tree of this graph is exactly what Nikhil showed. I'll root it at vertex 1. You have to root it somewhere, so we'll root it at 1. And then we just look at all the possible self-avoiding walks. So once you've gone from 1 to 2, you can then go to 3. 1 to 3, you can go to either 2 or 4. And once you've gone 1 to 2 to 3, you can either go to 4 or you can go back to 1. So here, this is a special vertex. We're closing a cycle. And similarly here, 1 to 3 to 2, you go back to 1 and close the cycle. And 1 to 3 to 4, it's a dead end, right? So now the really clever thing here is that whenever you close a cycle, you put a boundary condition into the tree. So so this will be a minus. It doesn't matter greatly, but they're complementary. So point is, we've closed this cycle in two different ways. So the cycle 1, 2, 3 back to 1, we've closed it in two different directions, either by this walk or by this walk. And those two different directions result in complementary boundary conditions at the closing vertex. Okay.
How do you choose which one is plus?
Based on a fixed ordering of the descendants of 1. Right. Okay. So now, the remarkable theorem is that the marginal RV, which is the probability in G that sigma V is plus, is exactly equal to the same marginal in the tree. So we're looking at the marginal probability of this guy being plus or minus. And this is this is exactly preserved when you go over to the tree with these carefully chosen boundary conditions.
Just 1/2 in this case, because we have no field.
Because we have no field, it will be a half, yeah. But not once we.
So maybe this is still true even if you have boundary conditions on the.
Even if you have boundary conditions on this tree, which will, in this graph. Yeah. Okay, so let's see. So now, how do we compute? So it's now, since this is a tree, it's pretty easy to compute recursively the marginal at the root. So the marginal at the root will be maybe it'll be this. So if we have the root vertex V and a bunch of children in the tree. D, by the way, D is, I'm just using as a D is delta minus 1. So it's a delta regular tree has arity. It's a D-ary tree where D is delta minus 1. So to compute the marginal at V, it's just the ratio of the partition function when I put a plus here and a minus here. And I can compute that, since these are independent subtrees, I can compute that from the same marginals at the leaves, at the roots of those subtrees. So I'll get, this will be, this is ZG plus over ZG minus, which is, since the subtrees are independent, it's the product of So when I put a plus at the root, then I get a contribution. So from each subtree, I get a contribution of Zi plus, which has no. So then I have a plus here and a plus here, so I have no beta term. And I also, in the case where I set this to be minus, I get a beta from the cut edge. And then it's the opposite way around on the denominator. And now I can just divide through by Zi minus to convert this into the form that I wanted. Okay. Okay, and so let's see. So I need to. There are two. So for the moment, let me omit the proof that the Weitz tree construction works. It works actually for any two-spin system. So not just for the Ising model, but for any system with two spins, because it essentially involves a kind of a telescoping product which works only for random variables that are two-valued. Let me now go to the second part, which is to argue that this recurrence actually converges rapidly so that we can cut off the computation in the tree at a logarithmic depth, okay, and thereby do the computation exhaustively on a logarithmic depth, which is a polynomial time computation. Okay, here's the right. So we're analyzing this recurrence. Okay. And so the first thing I want to do is change a variable. So R is going to, I'll write as, I'll write S is equal to log R. And so now my recurrence becomes, this product turns into a sum. So, okay. And so now I can use and let me call this G of S. Okay. So I can use the mean value theorem to write this. So certainly sorry, this is soup over. So, you know, the gradient certainly bounds the biggest value of the gradient on any given variable will bound the change in the function. Okay, the relative change in the function. So what we're going to show, the main calculation is to show that this thing is less than 1. So show that this is less than or equal to C, which is less than 1, provided beta is in the desired range. So beta is greater than beta critical. Greater than beta critical, which is delta minus 2 over delta. And that'll mean that you get a okay, so that'll mean that if you look at imagine two recurrences being carried out on the tree. The error at the parent node will be strictly less than the maximum value, or in fact it will be 1 minus epsilon times the error the worst error at any one of the children. Okay, so we have a contraction at every level of the tree, and so therefore, you know, after at depth L. So if I start off the recursion with two different sets of initial values here, and the depth is L, then the error in these two will be bounded by c to the L times the whatever the initial value was. Imagine that one of these is the perfect tree, the exponentially sized self-avoiding walk tree, which gives me the exact values. And this is just my computation that starts off at some arbitrary set of initial values. Okay, then I can ensure that I get a small error in the marginal at the root, provided my depth is large enough. So at depth L, you'll get that the let me call it this ratio the exact one R, and R prime my computational one. So this will be less than or equal to c to the L times the maximum error here. The maximum error here. So it seems that it could be infinitely large because when you have a plus or a minus boundary condition, the ratio is infinite or 0. But this recurrence maps, infinity to 1 over beta and 0 to beta. So in fact, I can always assume that the worst error on my leaves is beta to the d, or 1 over beta to the d. Okay, so this will be less than the max error at leaves, which is less than or equal to c to the L times log of 1 over beta to the d. Okay. And so I take L to be order n over epsilon. Then log n over epsilon. If I take L to be order log n over epsilon, then this thing will be as small as n over epsilon. Can people see down here? Probably not. Slide this across. Then the error is less than or equal to n over epsilon. So if I've got an n over epsilon error in the logarithm, that translates to a 1 plus or minus 4 n over epsilon, 4 epsilon over n error. Error is epsilon over n, I'm sorry. 4 epsilon over n multiplicative error in R itself. And from that, using recursion, I can get an estimate of the whole partition function with error about epsilon. And the running time will be, so the running time will be delta to the L, because I'm cutting off my recursion at depth L, and this is a delta, a graph of bounded degree delta. So this will be order, so this will certainly be polynomial in n and 1 over epsilon. All right, so I guess I need to do one computation, which is this one. Okay.
It's very important to use the L infinity norm here, right? Because you don't want it to depend on the number of leaves, which is also going up.
This one? Yeah. You can get stronger results with different norms. Actually, you can play with these norms and get. For example, you can get results with bounded average degree rather than bounded degree by playing with the norms. Right. So. So let's look at this guy. So we just have to sum the partial derivatives of this function. And if you do that, you get take my word for it, you get this. And so we want to maximize this, and the minimum value of this is 2. So we will get, 1 plus beta squared on the bottom, cancel out a factor of 1 plus beta, and you get 1 minus beta over 1 plus beta. And then there's a d factor coming from the summation. Right? And so this will be less than 1, provided d is less than, provided beta is bigger than d minus 1 over d plus 1, which is the same as delta minus 2 over delta. So, right, so that's the basis of a bunch of correlation decay algorithms. I guess maybe I won't go back and do, so the proof of the Weitz theorem is elementary and beautiful, but I may come back to it later. I have a minute. Right, so a few remarks. So this approach, again, it works for all, at least the translation to the self-avoiding walk tree works for all 2-spin systems. And in particular, so in the anti-ferromagnetic case, it still works, same argument. And the second part also works. So the second part, by the way, the second part is actually a little delicate, in fact, because the second part in general is really showing that, imagine the correlation decay on a tree really just says, okay, so for an arbitrary boundary put here, the effect on the spin at the root goes to 0 as this goes to infinity. But in the Weitz tree, we actually got these boundary conditions. So in fact, you not only need this this decay of correlations to hold with no boundary conditions, you actually need it to hold for general boundary conditions. And in particular, the boundary conditions, these pluses and things, can be very close to the root. So, so getting this to work in general, the second step, this decay analysis, does require you to, I mean, it does work in this simple case for no field, but in more elaborate applications, the fact that the decay of correlations with no boundary conditions actually holds also with boundary conditions arbitrarily close to the root. Of course, the boundary conditions are the same in the 2 copies of the tree, right? So the 2 copies of the tree, you've got the same boundary conditions close to the root. It's only the stuff far away that changes. But these things do have the potential to mess you up in general. And this is a question as to whether, some weak spatial mixing is the jargon for correlations decaying in the absence of any boundary conditions, and strong spatial mixing is the stronger property where you have where it also occurs even with boundary conditions close to the root. And so it turns out that when you're applying Weitz, so you can always, in a 2-spin system, you can always go over to this tree formulation, but your argument for decay of correlations may fail if weak spatial mixing does not imply strong spatial mixing. Okay? Now, it turns out that for the anti-ferromagnetic easing model, which is the thing I started to draw here, so for the anti-ferromagnetic easing model, this argument works, and it even works with a field up to the critical field for decay of correlations in a weak sense. And so for the anti-ferromagnetic easing model, you have and then for the anti-ferromagnetic easing model, you also have the fact that, so anti-ferromagnetic easing So you have, on the one hand, you have an algorithm for deregular graphs, for bounded degree graphs, whenever the Gibbs measure is unique, even with a field, unique on the delta regular tree. Gibbs measure on the delta regular tree is unique. Even with a field. And then in this case, you also have a complementary result that this is Weitz, and then Sly and Son prove a complementary result that outside this range of parameters, the problem, not only does the algorithm not work, the problem becomes NP hard. Right? NP hardness outside this. In the sense, this regime, in the sense that you can find, you can construct graphs of bounded degree delta such that you can't, you know, it's NP hard to approximate the partition function when the field and the beta and the lambda are in the range of non-uniqueness. Okay, so now in the ferromagnetic case, in the ferromagnetic case we can't hope for this because we know from the Markov chain Monte Carlo thing that we have polynomial time algorithms everywhere. On the other hand, you can't get the Weitz thing to work throughout the uniqueness regime with a field in the ferromagnetic case. It's a bit of a mystery that, but we can't do that. But in fact, this property fails in the ferromagnetic case. In the ferromagnetic case, you can stick carefully chosen boundary conditions close to the root, such that you do not get this decay of correlations property, even though you have uniqueness. Okay, so that motivates a little bit the last. So the last thing I want to talk about is this polynomial interpolation. So now so you're going to hear a great deal more about this from Sasha tomorrow. So I'm just going to do one example application, keeping with our theme of the Ising model. I'm just going to show you how it works for the Ising model, and then Sasha will, I'm sure, talk about many other examples tomorrow. Right. And the idea here is, right, so we've already used, we've already shown how to use correlation decay, which is one notion of spin systems being well behaved and not having a phase transition. We use that to get algorithms, and indeed in some cases to show that it represents a boundary of tractability. So the idea now is to look at the other characterization, the zeros of the partition function, and see if what we can get out of that algorithmically. So the lack of zeros.
So are there Markov chain algorithms in the anti-ferromagnetic case?
Yeah, so yeah, if you have strong spatial mixing, then you do actually have Markov. I mean, that actually implies that not on every graph. The graph has to be what's called amenable. So amenable means that the size of a boundary of a set is small compared to its interior, so like lattices and things like that. But obviously they don't go beyond what you can do with correlation decay, because correlation decay gets you everything you could hope for in that case. Yeah.
But you cannot match correlation. You cannot match out the correlation decay with Markov chain.
Well, on amenable graphs, yes, but not on, yeah.
Hard to mix some trees. Make your own chart.
Right, okay. So polynomial interpolation. Okay, so what we want to do is, right, so very simple setting for this here because we have the Lee-Yang theorem, right? So what's our goal is going to be to compute the partition function, compute the ferromagnetic easing partition function, approximately, of course. Which, you know, I've been writing ZG. So this is in the Lee-Yang parameterization, right? For all, and this is going to work for all lambda not equal to 1. So as we know, the zeros lie on the unit disk, so we're in this setting. Point 0, this is the unit disk. And we know that there are no zeros inside the disk. And what we want to do is compute this thing at any point in the disk that's, you know, in the strict interior. Right? And the beautiful but simple idea is just that, you know, no zeros in here, then the Taylor series of, a Taylor series of log z will converge in here, and indeed, you don't need to, it turns out you don't need to take very many terms of it in order to get a good approximation to this point. So you're going to essentially use it as a means of bootstrapping the value at 0, which is an easy point. So Z0 is an infinite field, right? So that's a case where, you know, basically everything is plus or everything is minus. It's equal to 1, in fact, when lambda equals 0. So we can bootstrap the known value of the polynomial at 0 to any point inside the disk using the truncated Taylor series. Okay. And so the fact from a very special case of general theorems of Sasha and Soberon, is this one? Just you. Okay. I'll erase the code. Okay, so that if we take a order log n over epsilon terms of the Taylor series, a series of log z around 0, will give a plus or minus epsilon approximation of log z. Okay. Where n here is the degree of the polynomial, and epsilon's the desired error. So this is the degree of the polynomial, which in our case is just n, the size of the graph. So again, I may or may not spell that out, but I'm assuming you'll probably do this. So, and once again, so a plus or minus epsilon approximation of log z will give us a 1 plus or minus multiplicative approximation of z itself, right, when epsilon is small. And so this is enough. Okay, so the algorithm is then very simple. You take the Taylor series, you truncate it at this many steps, this many terms, and spit out the approximation. Now, but there's some issues now. Well, there's an easy point. So how do you compute that? The Taylor series of log z. Well, you can compute it to compute its terms from the from the polynomial z itself, right? Using the there's the kth derivative of z is related to the derivative of its logarithm by linear triangular system. And so you can, to get the terms of the Taylor series of log, these things, you can dig them out from the derivatives of z, and this is all evaluated at 0. Evaluating the any derivative of z at 0 is just basically looking at its jth coefficient. Okay, so so getting the terms of the Taylor series is easy. Taylor series of log z is easy. Now the bigger issue computationally is that so how long does it take to evaluate all of these terms? So basically we're having to evaluate the first log n coefficients of the polynomial. Okay, and that could be bad because those involve all cuts of size. Right, so the first m coefficients involve cuts of size where there's at most m vertices on one side of the cut. Okay, and so naively computing those coefficients will require, order n to the m time, because there are by exhaustive enumeration there are n to the m of them. Just the number of subsets of size m from our vertex set. Now I think and we have to take m up. M has to be about log n, so this is n to the log n, right? So this is what we call quasi-polynomial. So of course, if you're a mathematician like Sasha, in fact, absolutely correctly, you believe that this is just fine. And in fact, so computer scientists would much prefer to have an n to the 100 algorithm rather than an n to the 0.001 log n algorithm. Okay, and since I'm a computer scientist, I'm going to shoot for this. Right? Yeah.
We need something that's closed under compositions, right? So that you can reduce and iterate.
Yes.
And from that point of view, polylog is just fine.
It's just fine. Okay, but indulge me just for. Yeah, yeah, right. Okay, and I mean, there are all kinds of arguments about how this involves additional structure and understanding and so on. So in this case, yeah. So beautiful idea of I guess Goose-Rex and Patel and shows us how to restructure this computation so that you only in fact need to look at cuts essentially in which S is connected. If S has to be connected, then the number of cuts of size m is no longer in a bounded degree graph is no longer n to the m. It's delta to the m. Right? It's sort of like this will be order n times delta to the m because if this has to be a connected subgraph, then you can just grow it with delta choices at every step. So how do you do that transformation? So that's I'll just sketch out Goose's original idea. There's a nice recent paper of Helmut, Perkins, and Regs that does this same trick, and I guess arguably more general setting using the cluster expansion, which is a tool from statistical physics that is a general way of getting from unconnected or disconnected arbitrary subgraphs to connected ones. So that's something that's very nice, and they've applied in other settings as well. So so let's see. So right. So let's write z as let's write z as so let's suppose the roots of z are R1 through Rn. So I can write z, since its constant term is 1, I can write it like this. And I can further write it. Okay, so this is the kth elementary symmetric polynomial evaluated at the roots, so the 1 over the roots. They're just expanding this thing out in the obvious way. So then okay, so these EKs, I mean, this is after all just the original polynomial. These EKs are basically just signed coefficients of the original polynomial. So these EKs themselves are sums over cuts. Okay, so the EK are so you can write them as, you know, sum over cuts of some weight. So now the idea is to use Newton's identities to relate the EK to the power sums of the roots. Okay, so I define PT to be the teeth power sum of the roots. Then I get from Newton's identities, I guess one form that I think was mentioned in Jan's lectures. So this one. So this relates the power sums to the e's. Now, the nice thing about the power sums is that they satisfy an additivity property. So the power sums. Okay, in the sense that if you look at so if you look at the partition function for two disjoint graphs, it's the product of the partition functions. So the roots are just the union of the sets of roots, and so these power sums just add up. Okay. And then there's a sort of general theory of graph invariants, and their representation as weighted sums over subgraphs tells you that so this is, I believe, due to Shikari and Frenkel. Is that correct? Yeah. Tells you that so a graph invariant, or represented in this way, is So Fg is additive in this sense if and only if it is supported only on connected subgraphs. I'm glossy that you have to get the exact definition of the set of graphs and how you have to account for the cut edges correctly and so on. And but basically this carries over, and so this is great because it tells us that these things can be computed just by looking at just as sums over connected subgraphs. And then you can use dynamic programming to compute the EKs, which is what you want, okay, from these identities. So since it's only over connected subgraphs, we only got a polynomial size support that we have to evaluate. So for each coefficient, each s, you got to find the coefficient alpha s of each s. Connected S, there are only polynomially many of them. For each one, you can read it off by dynamic programming from, a combination of, these things that are already coefficients are already computed, and these things which just come from the polynomial itself. So in polynomial time, you can actually read off the entire, all the coefficients of the original polynomial up to logarithmic depth. Okay, so the bottom line from all of this is you get a 1 plus or minus epsilon approximation, right, to z and sorry to z, z lambda for all for all lambda off the unit circle. And and this, you get this in time that's polynomial in well, okay, let me write it like this. It's polynomial in n over epsilon, and the dependence on the degree and on lambda is this. So you got the degree and the distance to the roots in your exponent. So of course this is going to explode when you approach the circle, and of course it explodes not quite so badly when the degree of the graph goes up. Okay, so I guess I'm going to. When am I supposed to finish here?
4:55.
4:55. Okay. Okay.
Including open problems.
Yeah. Okay. So, I was going to talk a bit about. Let me move that to the open problem. So I guess so I'm not going to do any more kind of main stuff. Are there any questions at this point, or should I? Or what I'd like to do is mention a few open problems and then invite people in the audience, many of whom know a lot more about some aspects of this, to propose any additional open problems. Okay. Right, so, I mean, very, very obvious, but probably not easy open problems, so we want a deterministic deterministic approximation algorithm, giving a 1 plus or minus epsilon approximation, polynomial time, for all, all values in the ferromagnetic range of beta, and at the bad value of lambda, so as we get to zero field, right? So there's no reason at all to expect that this wouldn't be possible, but we don't know how to do this. Okay. The Markov chain Monte Carlo method does work, so we have a randomized algorithm for this, but not a deterministic one.
Not for complex lambda, right?
Right, complex lambda.
But the Markov chain doesn't work for complex lambda.
Oh, I see. Yeah, no, the Markov chain doesn't work at all for complex lambda. Absolutely. Yeah. Right.
Even lambda equal to 1.
Sorry?
Even lambda equal to 1.
The Markov chain?
That
For
is
this problem.
Oh, you mean this is even this is interesting? Sure. Yeah. Sure. Okay.
So this interpolation approach works in the full range of beta, right?
The interpolation approach? It works in the full range of beta. Yes. It doesn't see a problem with it. Yep. And all degrees. We also don't want to bound on the degree, right? Now, so more generically, right? Both correlation decay and polynomial interpolation suffer from the problem that the degree and the distance to the roots, or in the case of correlation decay, the distance to the phase transition, show up in the exponent, and it would be very nice if we could prevent that. So even if the running time might grow with them, maybe we can improve that dependence. So improve dependence on delta and distance to criticality, if you like, criticality or roots. In all these deterministic algorithms, right? So in both correlation decay and polynomial interpolation, and this is not just for the Ising model, but in general. So this is a general feature of these methods that these things show up here, and there's a sort of fundamental question whether that can be improved. I should say, so in the case of the Ising model, our running example, again, we can do this interpolation anywhere inside the unit circle, and you'd like to do it at the point lambda equals 1, in particular on the real line, but as the graph gets bigger, you can even show that the positions of zeros actually get arbitrarily close to this real point. So you can't sort of, you don't really need a disk. I mean, you can, and I'm sure Sasha will talk about this tomorrow, you can thread sort of, as long as you've got a sort of a bounded width strip here, you can thread it to this point and still make the method work, but you're not going to be able to do that because these distances get arbitrarily small as the graph gets large. Well, you might be able to do it, but we don't currently know how to get over this.
Is this true for every point on the circle? That as you take larger and larger graphs, you can really get arbitrarily close to it?
I believe that as you get larger and larger graphs, the zeros become dense on the circle. I think. Is that right, Piyush?
Yeah, very strange.
Yeah, it would be very strange.
It would be, well, I mean, yeah.
Things happen.
Right.
Not such things.
So can you get, with polynomial methods, can you get the same thing you get with White's method on the anti-ferromagnetic case?
No, we don't, because we don't have a Li-Yang theorem there, right? We don't know where the zeros are. No, I'm sure you can do something, right? So Sasha's going to tell you about lots of. So here, the emphasis has been very much on getting right to the phase transition because that was how it's structured. But yeah, I mean, there are definitely non-trivial ranges for all kinds of problems where you can make that method work. Just not all the way in there. Okay. Right. So then. So again, continuing with the Ising model. So the Fisher zeros. So we looked a lot at the Li-Yang zeros. That they lie on the unit circle. That's the parameterization of the polynomial in terms of lambda. If you flip it around and look at the parameterization in terms of beta, then you get a obviously different polynomial, different bunch of zeros as the zeros in beta, and these are called Fisher zeros. So that's when you look at ZG lambda as a polynomial in beta. And these are much less well understood than the Li-Yang zeros. I mean, they don't, can't say a huge amount about them yet. Although there's a lot of work going on in general in locating zeros of partition functions. So this is so what we would like to do is get a full picture of where they lie. And I can tell you, so one thing that you can show, a couple of things you can show, is that, all right, so here we're looking at zeros and beta. So remember we have these complementary critical points for the ferromagnetic and the antiferromagnetic Ising model, and so this is the regime where there's uniqueness as a Gibbs measure, and you can show that one thing that Sasha showed was that there's a circle around 1 in which there are no zeros, no Fisher zeros, and another thing you can show is that essentially there's a strip a strip around this entire region of uniqueness in which there's no Fisher zeros either. So there's a strip like this in which there's no Fisher zeros. So the picture of Fisher zeros is gradually being put together, but it's a long way from being resolved. This actually gives you another algorithm. This gives you a polynomial interpolation algorithm analogous to the Weitz one for the ferromagnetic Ising model and antiferromagnetic one when you have decay of correlations. So this is relating decay of correlations to polynomial interpolation, if you like. So when you have decay of correlations, polynomial interpolation also works in this particular example. And there's a lot of beautiful work, which I hope sometime in the semester we'll hear more about, on mapping the zeros, for example, of the independence polynomial, or the independent set polynomial, in which similar kind of methods have been used, and the picture is also emerging rapidly there. Okay, so similar, right? So independence polynomial also. Okay, and then let me also suggest that so we have these methods, Markov chain Monte Carlo. We have correlation decay, and we have polynomial interpolation. I'm not suggesting these are the only. I mean, very recent work of Nima and Cheyenne using high-dimensional expansion is another approach. Is Leonid here? Okay, so there's a lot. There are other methods. I'm not claiming these, but these are three very widely applicable methods that tend to have nice interpretations in these statistical physical models. And the question is, what kind of relationships can we establish between them? We already know quite a bit, as I mentioned before. Fairly tight connection here when graphs are amenable, and this much newer method, I've attempted today to briefly mentioned very tenuous connections between it and correlation decay via results like this. And even more tenuous connections between this and Markov chain Monte Carlo via that stuff about like the log concavity of the coefficients. So, you know, these connections here are pretty wide open in general, or even in specific cases. And finally, let me mention, you know, so the So I've talked a lot about the Ising model. Another problem where we have a somewhat similar situation in a sense is the permanent or perfect matchings. And okay, so this is the top coefficient of the matching polynomial, and there's all kinds of other important applications. So this is, here we have a situation where a lot is known. So we have randomized and deterministic algorithms for computing the whole polynomial, the whole matching polynomial. So without the perfect in there. So evaluating that polynomial.
Randomized is much better, right? Just for the number, not for the weighted.
Well, actually, randomized is better in the sense that it doesn't require the degree to be bounded, for example. Yeah. Yeah. So it's sort of a similar situation to the Ising model. So we have a Markov chain Monte Carlo algorithm for matchings and indeed for the permanent, right? So we have a good randomized approximation algorithm of any matrix, permanent of any matrix with positive entries, with non-negative entries. So once again, you know, this is what we have to beat, but we imagine that it can probably be de-randomized, and we know a lot already about the structure of the matching polynomial. So I say we have deterministic algorithms for bounded degree matching polynomial, not the permanent, but the matching polynomial. And so, what can we do about the permanent deterministically? So, you know, you'll hear a lot. You have heard quite a bit already